Hello everyone, myself R. Aishwarya. My register number is 17V10. Let us see about speed control of three-phase induction motor. First, what is an induction motor? It is an electromechanical device that converts electrical energy into mechanical energy. A three-phase induction motor is most widely used motor as it does not require any additional starting device. A three-phase induction motor has two major parts. One is stator and other one is the rotor. And here it is the stator windings and here it is the rotor, and the three-phase supply is given to the stator windings. First, what is a stator? A stator has a number of slots to construct a three-phase winding circuit which we connect with a three-phase supply. And then rotor. The rotor consists of cylindrical laminated core with slots that have conductors. And these conductors are made up of heavy copper or aluminum bars and they are short circuited by end rings. Let us see the working principle. The motor works on the principle of Faraday's laws of electromagnetic induction. Initially, the rotor conductors are stationary and the magnetic field is rotating in nature, and therefore there is a change in the flux linkage, so that there is an induced current in the rotor. As we know that a current carrying conductor inside a magnetic field experiences a mechanical force, and this force causes the rotor to rotate inside the stator, and this rotor always rotates at a speed slightly less than the synchronous speed for continuous rotation. And then slip, and the slip is given by the difference between the flux ns and the rotor speed. Then the percentage slip is given by ns minus n divided by ns into 100, where ns equal to synchronous speed and n equal to actual speed of rotor. And then the slip speed is given by ns minus n. And then speed control methods. First of all, what is the need of controlling the motor speed? As we know that motors are used in different applications, and in different applications they are working at different speeds. For example, in some type of loads they require constant speed, and for some type of loads they require variable speed. For example, in traction motor, let us see the categories. First, from the rotor side, and second one is the stator side. First, the stator side. We have four methods: B by F control or a frequency control, or by controlling supply frequency, or adding rheostat in the stator circuit. And the last one is changing the number of stator poles. It has two methods: multiple stator winding method and pole amplitude modulation method, which is known as PAM. And from the rotor side we have three. First one is adding external resistance on rotor side. Second one, cascade control. And the third one, injecting EMF at slip frequency into the rotor side. Let us see about adding external resistance first. In this method, external resistance are added on the rotor side. As a result, the torque equation becomes T is directly proportional to SE2 square R2 divided by R2 square plus SX2 the whole square. And this motor usually operates in a low slip region. Because of this, Sx2 square becomes very small when compared to resistance R2. So we can neglect Sx2 square. And also E2 is also constant. So we can neglect. As a result, the equation becomes T is directly proportional to R, and R gets cancelled. So the equation is S divided by R2. Suppose if we increase the rotor resistance, the torque decreases, because torque is inversely proportional to R2. Because here we are using the same load, the torque should remain constant. To compensate this, we are going to increase the slip, which will result in the decrease in the rotor speed. As a result, in this method, we can decrease the speed of the motor. This method has an advantage that the torque gets increased, but this method has some disadvantages. Let us see one by one. First one, the speed above the normal value is not possible, and because of the large value of resistance, there is a large copper loss. Therefore, there is a reduction in the efficiency, and because of the resistance, there is a I square R losses, and this method is not applicable for squirrel cage induction motor, and it is only applicable for slip ring induction motor. Okay, and then cascade control method. In this method, we have two motors. One motor is called the main motor, and the other motor is called the auxiliary motor. Here, it is the main motor, and the motor B is the auxiliary motor, and they are connected by a common shaft. And a three-phase supply is given to the motor A, and the motor B gets applied from the slip rings, and it is the load. And then NS1 with the synchronous speed of the main motor, and NS2 with the synchronous speed of the auxiliary motor, and P1 and P2 be the number of poles of the main motor and the auxiliary motor. F is the supply frequency, and N is the speed, and here it's the same for both the motors as they are connected on a common shaft. And then S slip is given by S1 is equal to NS1 minus N divided by NS1, and we have three cases. In first case, the supply is given only to the main motor, so that the synchronous speed is given by 120 F by P1. And in the second case, the supply is given to the motor B alone. So the synchronous speed becomes NS2 equal to 120 F divided by P2. And the third case is cascading. Cascading means adding. In this, cascading two motors will result in the adding of two poles such that N equal to 120 F divided by P1 plus P2, and these stator fields of both the motors are in the same direction. The last one is differential cascading. In this, the stator fields of both the motors are in different directions. As a result, the synchronous speed becomes N equal to 120 F divided by P1 minus P2. Okay? And this method has some disadvantage. That is, it requires large space and it requires two motors. And this is the disadvantage here. And the last method is injecting EMF at slip frequency into the rotor side. As in the last method, there is a loss of power, and this power is known as slip power, which is lost as I square loss or losses. Because of this, efficiency gets reduced. To overcome this, we are introducing this method, that is injecting EMF at slip frequency. In this method, we inject external EMF into the rotor through slip rings, and this method is possible only in slip ring induction motor. In this, we control the motor speed in two ways, that is below the synchronous and above the synchronous speed. First, below the synchronous speed, that speed is known as subsynchronous speed. If we control the speed above the synchronous speed, it is known as super synchronous speed. And the main advantage of this speed control is that the speed control is possible below and above the normal speed. Let us derive the equations for subsynchronous speed and super synchronous speed. First, as you know that torque is directly proportional to S E2 square divided by R, where S is the slip, E is the EMF, and R is the resistance. For subsynchronous speed, in this, the EMF induced in the rotor and the EMF injected at the rotor are acting in the opposite direction, so that the net EMF becomes ER minus E injected. If E, that is net EMF, get reduced, the slip will get increased to compensate this. As a result, speed gets increased. And for getting super synchronous speed, we have the following condition, that is the ER and the E injected are in same direction, that is the EMF induced in the rotor and the injected EMF are in the same direction. So the resultant EMF gets added, that is ER plus E injected. In this, as we are adding, the E becomes increased and the slip gets decreased to compensate here, and the speed gets decreased. And then moving upon to the application, as we all know that three-phase induction motors are used in many applications such as traction, lifts, cranes, and driving lathe machines, crushers, oil extracting mills, textiles, etc. And thank you for listening.